Alright, so today we're going to talk about lesson 7-6, function notation. And function notation is another way to write an equation. Okay? When a function f contains the ordered pair x comma y, then y is the value of the function at x. And we may write y equals f of x. So, in essence, we're used to writing equations like this. Okay? Function notation, this is just a linear line. Function notation replaces y for f of x, saying this is a function in terms of x. So this is a function f in terms of x. And what you should notice is basically everything's the same thing. So if I put 1 in for x here, what I get out is 1 times 3 is 3, minus 3 is 0. Well, when x is 1, y then is 0. Same thing here. If I say, what is f of 1? If I put in 1 for x, 3 times 1 is 3, minus 3 is 0. So once again, I still get out the same coordinate. My x is 1, my y is 0. And those are coordinate points. If you want me to refer to like yesterday, input, output. I input 1 to get my output 0. Refer to the graph on page 397. Recall that each equation represents a different prediction of the population of a town X years in the future. Each model describes a function. The functions are 3 types. If you look at this, possibility 1, P equals 100,000, describes a constant function where the population does not change. This means the population always stays at 100,000. Never goes up, never goes down. Okay? Since this is a constant function, I could call this C of x is equal to 100,000. C being my constant, x being any number, but I'm always going to get out 100,000. Possibility 2, P equals 100,000 plus 3,000x. This is a linear function. Why? 3,000x is my slope. This is my y-intercept. Okay? I could call this L of x. Okay? Linear function in terms of x, 100,000 plus 3,000x. Notice that 100,000 is my starting value, and then my population is going to go up 3,000 people per year. Okay. Possibility 3. 100,000 times the quantity 1.02 to the x power. This is an exponential function because I have my starting value, I have my exponential growth factor raised to the x power. So we could call this E of x, because it's in terms of x, equals 100,000 times 1.02 to the x power. Now, why is it okay to do this? Well, just for instance, what I can do is I can determine which is which when I type these into my calculator. I know this is my constant function, I know this is my linear function, I know this is my exponential function. Okay? It's just a way to separate these different types of equations. Let's look at f of x notation. Okay? Conveniently, mathematics does have another way to name functions. This method, the possibility 3, can be written E of x is equal to 100,000 times the quantity 1 plus 0.2 to the x power, as Mr. Johnson just showed you. So if I wanted to find something that was 20 years down the road, okay, I would put, and I would find what's E of 20, because X is 20. So then I would take that equation, 100,000 times the 20, 1.02 to the 20th power. And so 20 years down the road, when X is 20, my output is 148,595 people. Let's look at example 1. It says, given a function with the equation f of x is equal to 5x minus 19, find f of 2. All f of 2 means is put 2 in for x in the f function. Well, this is my f function, f of x. So wherever I see an x, I'm going to put in the number 2. So f of 2 is equal to 5 times 2 minus 19. What's 5 times 2? 5 times 2 is 10. Minus 19 is a negative 9. Now I can also put that in a coordinate point. What was my input? My input was 2. What was my output? My output is a negative 9. X value, Y value. Input, output. Moving along, example 2. It says use the 3 functions given earlier for the population models to find E of 10, L of 10, and C of 10. Explain what the results mean in the context of the population situation. What I'm going to do is I'm going to type those 3 equations into my calculator and show you just how convenient this is. So, I'm going to pull out the sheet that we used before. Here's my constant function. Here's my linear function. Here's my exponential function. Okay? So I'm going to go CLE. Okay? So C is 100,000, so I'm going to type that in there. Okay? My Y2 is 100,000. Plus 3,000 x. My third equation is going to be my 100,000 times 1.02 to the x power. Now, I'm going to go to my table setup here, so second function window. It's going up by 1, so that's what I want. And I want to know when each of these, when x is 10, what does these functions equal? So I got C of 10, I got L of 10, and I got E of 10. Okay? So, I hit second function table, because all I'm going to do is I'm going to scroll down to when x equals 10. And I'm right here. Okay? At 10, no matter what, for our constant function right here, y1, for our constant function, no matter what value of x I put in, I always get out 100,000. The constant function is saying that the population never moves. In 10 years, with my y2 function, that's my linear function, it says my population is going to be 130,000. So in 10 years, what they're saying is that my population went up 30,000 people. Stayed the same in 10 years for the constant function. For my exponential function, I got to go over here to my y3. And my exponential function says that my population is, according to that model, 121,899. So I gained, it went up 21,899 people. And that's how you can use these three different equations and your calculator to determine what 10 of the constant, the linear, and the exponential function is. So let's look at example 3. Possibility 2, use the linear function L of x is equal to 100,000 plus 3,000x to model the population of a town x years in the future. According to this model, in how many years will the population reach 150,000? So what I'm going to do is go back to my computer, okay? And what I want to do is I want to find out when my y2, because that's what we got our function in, when my y2 equals 150,000. Okay? Notice this is my output. Okay? I'm trying to find the input x. So I'm going to go back to my computer, or my calculator, sorry. And I want to look at my y2. My y2 is right here. That's my linear function. And we want to know when that's going to equal close to 150,000. Well, about right here. Okay? Here it went from 148 and then jumped to 151. So what you would say is probably 16 to 17 years. So you would say approximately 16 and 2/3 years, because it looks like it's gaining 1,000 people every third of a year. So 16 and 2/3 years is how long it would take to reach 150,000 people according to our linear equation. Okay? Example 4. For e of x equals 100,000 times 1.02 to the x power, use the graph to find when the population reaches 150. Well, we knew with our linear deal that it reached 150,000 in 16 and 2/3 years. Okay? If we look on here, this is our e of x function. That was nice of them to graph it for us. We want to know when it equals 150,000, so I go across here, and it looks like it equals 150,000 right at this point, which is at year 20. So at year 20, it reaches 150,000 people, which is a lot slower than what our linear function was, because our linear function reached it in 16 and 2/3 years. Unless the situation suggests a better letter, the most common letter used to name a function is f. Okay, that's just normally what your book uses. That's why we call it the f of x notation or function notation. We call it f of x. That is, instead of writing y equals 3x plus 5, we might write f of x equals 3x plus 5. Like I said, these two things are the same thing. Then f is a linear function with slope 3 and y-intercept 5. This is still your slope. This is still your y-intercept. It is read f of x. We read this f of x. equals 3 times x plus 5. This way of writing a function is called function notation, or f of x notation. The symbol f of x is attributed to the great Swiss mathematician Leonhard Euler. You call that Euler. O-I-L-E-R is how you pronounce that. Okay? Thank you for watching this video. We'll see you tomorrow.